Hi, good morning, everyone. Hope you're still okay. Remember, you
Good
can check
morning.
out. Yeah, you can log out anytime you want. If you need to sleep or do anything else, it's fine. I'm recording this on my computer, and it's also recording on the cloud via Zoom. So there should be a brain on your screens. Do you see any brain on the screen?
Yes po.
All right.
Yes po.
Yes, bro.
All right. Thank you for looking at the brain. That's the lecture for this morning. And what's the first word that you see? Okay, you don't need to blurt it out loud. No? So just keep it to yourself. This is it's just an opening slide. No significance to this. Okay, now look at the screen for around for until I click the next slide. This is just to emphasize a point. Okay. So I think you have all looked at the screen for too long already. So you should be seeing some form of optical illusion. So that's your brain playing tricks on you. The screen is actually motionless, but you're seeing some kind of movement from inception. Right, learning outcomes. So I guess from your feedback from the sensing forum, you want to go over this again later on. So the first thing that you want to learn is that the brain is arranged in regions. Okay, can you repeat in your minds? The brain is arranged in regions. It's arranged in a logical fashion. Everything is there for a purpose. Okay, so that's why we have so-called gyri, and you have certain parts of the cortex that do certain things. So there are such things as primary cortices, which do something special in particular, and there are association cortices which make sense of what that primary cortex does or understands. Next, you will more or less know what why there are fibers in the brain. Why do they go in different directions? Why do they cross the brain from right to left? Why do they go from the brain to the spinal cord to your peripheral nerves to your extremities? Or vice versa, from your skin back to your sensory nerves, back to the spinal cord, back to the brain. And then there are the in-betweens. So the association fibers, which connect different parts of the brain within each side of the brain. So more details on that as we go along. So I'm pretty sure you were bombarded with embryology of the brain and spinal cord from Dr. Batikalon's lecture. So the only thing I want to emphasize here is that your brain is hollow. So meaning there is fluid inside. So this is a concept that you'll have to remember when we're looking at cross sections. So if you're cutting a tube cross sectionally, it will look different from a tube that you cut longitudinally or from side to side. So this is a brain looking at it from the front. So I'm pretty sure you've been oriented on antero-posterior orientations, or if we're talking about the head and the brain, it's coronal. So you're looking at it from the coronal point of view. And when you cut it in sections, from the side, from your right ear to your left ear, or vice versa, you get sagittal sections such as these. So going back to the emphasis of this slide, your brain is hollow. So there's fluid inside. Right? So it's a tube before, during embryonic development, then it becomes something a lot bigger than a tube. So if you follow from below, going internally, so from a very longish looking structure, it curves and curves and curves upon itself, noting that different parts of that embryonic brain will grow at different rates. So the front part of the brain will grow exponentially more than here in the brainstem. as you follow along towards nearing childbirth, the brain will expand. I mean, the telencephalon or the cerebral hemispheres will expand and expand and expand until there's no more space left to expand. So, with no more room left to expand, it needs to fold and fold and fold upon itself, forming the wrinkles that you see when you have a stereotyped image of a brain in your minds. And in so doing, that cerebral cortex covers everything else underneath. So there are gray matter that are growing inside that telencephalon, but they were covered up by the mantle that we call the cerebral cortex. Now, evolution should be understood in the form of divergence. So some species stopped at a fairly basic looking brain with no wrinkles at all. So small skulls with unwrinkled brains. Then you get bigger crania. Still, this reptilian species did not bother to expand its brain. That's you go on to the mammals, which had to learn a lot more things like moving around dexterously. So you have these primates, and you have these rodents, canines, and felines. Then you have these aquatic mammals. So they need to do learn. They needed to learn new things and perform things differently. Thus, the need for more brain cells. Hence, the they form their brains in similar ways, which are wrinkled brains with more surface area, more neurons inside. So, in that development, when the skull encages, no, it imprisons that expanding brain such that the structures will have to fold and fold upon themselves. So another way of looking at it, so a cross section of a neural tube type of embryonic brain during 5 weeks of age of development, which expands exponentially in front here in the telencephalon. So telencephalon includes that cerebral cortex as well as the gray matter in underneath that cerebral cortex until expanding until this gray matter inside are already enveloped by the gray matter of the cerebral cortex and its white matter. So I think this will be lectured to you by Dr. Baticolon. The hollow thing inside, that's fluid. Fluid shaped like this because of the foldings of the gray matter and the white matter around these cavities inside the the brain, the so-called ventricular system, which contains your cerebrospinal fluid. Now, those gray matter which were trapped underneath are what we will lecture on in a different time. The basal ganglia. Technically a wrong term, but it's the name that stuck. So it's a basal nuclei inside of the telencephalon. So, concept, you have cavities of fluid inside your brains, and then you have gray matter trapped inside your brains, and then you have the white matter of that cerebral cortex covering up these cavities and gray matter. So, knowing that would explain why when you cut a brain from different angles, you will see a pattern of gray matter on the outside and white matter on the inside. So this is what we try to imagine when we're looking at brains that have already been cut. Or before you cut a brain, with your X-ray vision, you say, okay, inside that brain there will be cavities shaped like this. So we will be cutting through it at different, as you slice the brain from front to back, they will look very different. So certain cavities will appear larger when it's over here, become smaller, and then become larger again, and then taper off again in terms of the size. So certain slices you'll catch those gray matter inside. Certain slices you will not see any gray matter because you have not reached it yet. So bearing those concepts in mind, we will go into that into detail later. So they've managed to grow brains inside the laboratory. So this is just a matter of manipulation of stem cells and differentiating factors to direct them to the path of what would become gray neurons and axons and astrocytes inside the brain. Okay, back to the brain. So there is gray matter on the outside. So this is based on anatomy, based on ancient Greeks cutting open people's brains and say, oh, why is it pink gray on the outside? And then when we cut deeper, it looks a lot paler on the inside. So that's where we got the concept of gray. Although technically it doesn't really look gray in the real world cadaver when you first the person just dies. No? So gray on the outside, white on the inside. And then if you look down here, you have gray buried deep inside. And then you have these hollow cavities here, which are the ventricular system. So gray matter on the outside, if you can imagine a big sheet of cloth or a blanket spread over a big area. And then you had to crumple it, forming folds over here. So mantle or cloak or anything that you spread over something else. So that's the origin of the word cortex or cerebral cortex. On the inside are the so-called white matter. So these are actually the extensions of the cells found here in the gray matter. So white matter, these are all fibers. So the distinctness of the brain compared to the other tissues that you've learned so far is there's no skeleton inside. An actual brain without formaldehyde will just be a piece of taho or tofu. So it's really of that consistency or a hard-boiled egg white. So very soft, and what we're looking at here is actually this is a snapshot of what the brain was in life. So I always like to show this to demonstrate the white matter versus the gray matter. It's very similar to a cauliflower. Well, it looks like a brain when you buy it in the supermarket, and when you cut it open, it also looks like a brain when you cut it on cross section. So I mentioned there were gray matter that were developing together with the cerebral cortex, but it's just that the cerebral cortex expanded exponentially, much more than these gray matter that you see on the inside. So they are gray matter, they look gray on your screens. So those are the subcortical gray matter. They correspond to these egg-shaped structures over here, colorized by Dr. Sunstein, which is captured in the book of Nolte. And just demonstrating this hollow cavity here, hollowness, or the cavities that you see here, which contain fluid in life, and reproduced here in terms of a 3D model. So the configuration is such because of the gray matter inside and the white matter that is on the outside of these cavities. So they are shaped by this white and gray matter. So similar to a tomato that you cut in a cross section. So in a coronal cut of a tomato, you see these cavities very similar to the ventricles that I showed you earlier. So very juicy when you cut through it. So we assume you all have different backgrounds. So this is tabula rasa. We don't expect you to know everything at the beginning. So we start from scratch. So what you see on screen is vaguely what you think a brain looks like based on what you've watched in cinema, what you've seen on social media, or what you've seen in the anatomy books. But what does it all mean? Why is it like this? How do you make sense of it? Where is the front? Where is the back? Where is the bottom? Where's the top? So of course there'll be clues. No? So there are certain things in life that are constant. There will always be a smaller type of brain here called the cerebellum beneath that cerebral cortex. So wherein you would know where the top is. So above that cerebellum is the cerebral cortex. Therefore, this is at the back of your heads. But more on that later. So everything today is going to be lectured as if you're a 5-year-old or at most a high school teenager. Right? So a actual cadaver, so which has already been fixed with formalin. So that's what it appears like. Not actually gray, but more of pinkish gray, covered by a film of Pachymeninge or the pia mater, which must have been lectured by Dr. Baticolon. Alright, so that's the skull on the outside. So that is what we think a brain looks like. So more or less that is correct. You see folds and folds of this tissue inside of the skull of this person. So these are actually made, these are tissue. So if they are tissue, they must be made out of cells. And if these are cells, these are nervous tissue, which I'll be lecturing on later on this week. Neurons which have very long extensions, which are the axons. So more on that as you go to neurohistology. Okay, and on the inside, it looks a lot whiter. So if you remember histology and the techniques we do to make those histologic specimens, we dehydrate them, we take out the fats. So the fats are cleared, as you see in this specimen. So this makes you deduce that the white thing that you're seeing here contain a lot of fat in life. So knowing that there is fat here means for some reason the brain cells need fat inside the brain for a purpose. So if you have some inkling what the brain does, it runs on electrochemical energy. It means something must be here for a purpose, most likely insulation. So this is myelin wrapping around those extensions of those brain cells here. So we call that myelinated axon. So due to the fat content, they appear as clear on microscopy, and they give that white appearance, hence white matter. Now, if you took out all the neurons and just left their axons, this is what your brains would look like. So very difficult to replicate this, but we've tried it in the laboratory. You painstakingly remove the cortex, you get this appearance. This is the white matter of the cerebral cortex. So again, it does not really make much sense when you look at it because it's so complicated. So we try to break it down. So we said at the start, certain parts of the brain do certain things. And since they have their cytoplasmic extensions, these will have to connect with something else. So certain parts of the brain are in charge of moving your extremities. Certain parts of the brain are in charge of sensing pain, sensing vision, sensing auditory stimuli. So these are going back to the brain. If you look at the brain under the microscope, it's really a mess of cells inside, arranged in certain layers. And it's the arrangement of these layers that tells the histologist what part of the brain it came from and what it actually does in life. So if everything is there for a purpose and everything is there for a reason, then there must be some logic to it. So if you have motor parts of your brain, therefore you must have something that moves your face, moves your mouth when you talk, moves the vocal cords that you learned in OS 204, moves the extremities of the muscles of the upper X and the lower X. At the same time, to make much sense, you also need to feel what you're moving. Hence, you also have assignments on the sensory side. So you have assignments for your legs, you have assignments for your arms, and for your head, each on one side of your brain. controlling the other half of your body. The reason for which you will deduce quite soon. So if this is the right side of the brain, so it's motor and sensory, these correspond to the left leg, the left arm, the left side of your head, and the left, whatever you feel on the left personal body space. And you have two of these to make a complete whole. So this gives you an internal map of who or what you are as a person. And you need two of these to form a complete whole of yourselves. So that is one reason why they're there for a reason, and why they're a pair of each on opposite sides of your brain. So you have two halves of your cerebral hemispheres. It all goes down back to the layers. So there are 6 layers. Again, those of you who have taken up nervous tissue before, this is your chance to learn it again in detail, since I did not really go much into detail in the pre-med course. So that's why every one of you are on equal footing in terms of this particular concept. There are 6 layers of histologic tissue in the cortex, in the cerebral cortex. So again, this picture really does not make much sense. It doesn't really, you don't see layers in 6 rows. No? You just have to imagine it. So the reason for this layering is just a matter of where you find certain types of cells. So if you see a certain set of cells here, then that should be layer 6. If you see a certain number of neurons here, then that's layer 4. But looking at it as you see it on the screen is actually how it looks like in the brain. It doesn't really look anything like this. Right? But someone actually painstakingly mapped out those layers. No? So some ancient histologists looked at, layer 4 and layer 6 seem to be particularly thick, depending on which part of the brain it was taken from. So here, certain the layer 5 particularly had large cells inside it, which was not found elsewhere. So in the 5th layer, and then going behind this certain groove over here, there's more of the layer 4 that was thicker. So based on what they saw from soldiers that who had spears in their heads, who managed to survive, they had numbness on one side, or they were paralyzed on one side. The spear was stuck, or the knife or the sword was stuck here, and the soldier was paralyzed. Here, they can move, but they don't feel anything on the other side of their bodies. So more or less by deduction and by histology, certain parts of the brain are for motor, certain parts of the brain were for sensory. For those who had a spear stuck to their brains here and managed to survive, they cannot see anything. So therefore, this part of the brain must have something to do with vision. So on and so forth. So everything we learn in neurology is trial and error, at least before. So it just depended on how thick those layers were in certain areas of the brain. So I mentioned that the cells needed to have extensions of themselves, and these were quite very, very long, which should reach from your head to your toes. And they had to be arranged in a certain fashion which was logical, meaning the legs were next to the arms, and the arms were next to the neck and then the head. And this pattern is maintained as that tract of white matter travels in your brains, into your necks, into your spines, until they reach the peripheral nerves that you learned in OS 203. So these are what we call tracts, and you will understand this as we go along. So they follow a certain pattern, and they must go in the same direction. So they will be arranged in certain layers. So what we call laminate. Those of you who know what lamination means, those who go to the bookstore to laminate their folders or whatever certificates. So layers and layers of plastic. So here, layers and layers of axons or dendrites. as you will learn soon in histology. So I mentioned the complexity of the brain depends on how much sophistication that certain animal needs to perform its day-to-day survival activities. So certain more cunning form of animals will have more specialized brains. So very intelligent, well, quote unquote intelligent animals which can learn complex tasks happen to have a large a reservoir of neurons in their heads, so in their brains, same as this guy. So this is a brain. So I'm showing you a brain cut 2 years ago. So it's all about pattern recognition. So where is the front? Where is the back? Where is the top? Where's the bottom? So the cerebellum has been removed from this specimen. So you do not need to memorize these grooves and these ridges. We only expect you to know more or less where certain functions are located. So we break it to you gently and carefully. But this is a brain. This is a human brain. And what you can see on your screens is that it has wrinkles. It has grooves which are deep in some areas. You have grooves that seem to follow all the way from the top to the bottom, and some which seem to disappear and then continue on later on. So this is one thing to remember about your atlases. They are not real. So they are ideal. So those grooves are not as perfect as you will see in the actual brain specimens. So level your expectations. So they will not be what appears in your netters or whatever atlas you're looking at. But certain things are constant. And this is a concept I will explore more deeply when we talk about neuroplasticity. But certain areas constantly perform something. So here in front, in the front part of the brain, has neurons which are dedicated for movements. One neuron is the one muscle. So whichever parts of your body has more sophisticated movements, like your fingers and your mouths, or whatever part of your body you're very sophisticated at, has a lot of dedicated neurons assigned to it. So the more fine detailed movements it is assigned to, the larger the area consumed or occupied by those areas in your brains. For example, the legs. So the legs, your toes are not that needed much they're not prehensile. You don't, well, unless you have trained yourself due to the lack of arms, you don't really need to use your toes to pick up objects from the floor. But some of you might have better skills at picking things up than others. So it depends how much neurons are there. And since, again, if a person was born without arms, then a lot more neurons are assigned to the movements of those toes because they were born without arms. So that's why we say more or less the areas for the legs are here, although it can stretch back down here depending on how dexterous the person's feet and toes are. Same thing with the arms. This is the opposite side of the body. So we are on the left side of the brain. This is the right arm being controlled by that portion. So again, the more dexterous it is, and the more you train your brain, more neurons will be assigned to more particular peripheral neurons down here in the spinal cord to specific muscle groups or muscles. As you go down here to the thumb, it has a large representation here in the lateral portion of your frontal part of the brain. But as you go down to the mouth and the head, a large assignment is found here, especially for the tongue and the lips. So very dexterous parts of your body. So most of you can form a curl with your tongues or contort your faces. That is a function of how many neurons have been assigned to those muscles. And in humans, those that can speak, in primates that can make sophisticated sounds. So you have a larger assignment of neurons here in front of that motor part of the brain. So a dedicated speech area here in the front, the inferior part of the frontal part of the brain here. Take note, I'm not mentioning any lobes yet. I'm just telling you, as you reach to the front parts of the brain, that has to do more with movements. And as you go more and more in front, this has to do more with actually sophisticated planning of those movements. So again, this can be trained. So those of you who cannot dance can be taught how to dance. And there are people who know how to dance better because they have trained their portions of the brains here. Or those with very good hand-eye coordination, those of you who play sports. Again, the brain is very plastic. It adjusts to the need for assignment of those neurons. They can be reassigned. So that I'm already mentioning to you plasticity of the brain. Hence, I'm not really focusing yet on the particular structures that you see colored here in the screen. So, more or less, here at the beginning of your lecture on the cortex, every one of you there who is listening in the audience who is not asleep yet knows that this front part of the brain is in charge of movements. And as you go further down here below, that is in charge of your actual speech production, word production. Okay, so speak. Then, behind that motor area, since anything you do has to have some form of feedback. So you cannot move properly if you have no feedback of where your arms are in space. No? If you're reaching out in front of you and you're trying to kill a mosquito, the distance from your face to the mosquito varies. So you need some feedback from your sensory part of the brain, which is conveniently located just behind that motor part of the brain. So again, assignments are there. So the parts of your body that need extra attention in terms of sensory feedback have more neurons assigned to it. So here for the legs is up here near to the midline on the top of the brain. And then as you reach down, similar to that area for the arms and the hands, a corresponding area here behind it, right? So for your arm and hand movements. And then as you reach down further towards this very deep groove over here, corresponding to the head and the face area here in the front part of the brain, here behind that front part of the brain, you have an area assigned for the face as well. So just to mention it here, for those people who had their limbs cut, let's say they lost an arm, so they can sometimes feel that arm still there because those arm area neurons have been taken over by most likely the face areas here, because the brain abhors a vacuum. So the brain needs completion. So that's the reason for the autocomplete function of your smartphones that is derived from your brain's autocorrect or autofill function. So that's for the face. So what's down here? So there must be a counterpart for this speech area here for talking. But for you to talk, you need to have feedback if what you're saying is correct. So you need to make sense of the sounds. So that is the auditory part of the brain over here on this part of the brain which is right behind your temples. So this temporal part of your brains is in charge of hearing, which makes sense. So there must be some form of communication between these speech areas and these language areas around this area here of the temporal part of your brain. So this is the frontal part of the brain, and this is the temporal part of the brain. This one we will not give a name yet. Then over back here, near your occiput, the back of your heads, this is in charge of vision. So a super specialized kind of sense. So it's the special sense, just like this is a special sense, the sense of vision. So what's all these areas about? So if we have this primary cortex for sensation, a primary cortex for hearing, a primary cortex for movement, you have an association area here for the face and arm and mouth movements here. So this is an association area over here. It makes sense of what is being said based on the feedback from this part of the brain. So the areas around these primary cortices will now be the association cortices, meaning they make sense of what these primary cortices do. Now by deduction, the area around this hearing area, so around that area, makes sense of what is being heard. So that is the language area for understanding and comprehension. Here behind that primary cortex for sensation, it makes sense of what you're sensing. And then you have this primary cortex here for vision. Then this area here and this area here, which is part of the temporal lobe, also tries to make sense of what you have just seen. Have you seen it before? Do you remember seeing it before? Does it evoke a certain emotion or experience from before? So this area of the brain, so frontal, temporal, occipital, and this area around here. So in Latin, the area around here is parietal. So dito banda, so parietal. So this is what is now called parietal lobe of the brain. You don't see any particular markings which will really tell you where it is, except for a certain groove here in the front. So we'll get to that later. So now this part of the brain makes sense of everything that you're hearing, feeling, moving, and sensing all at once. So this is where your inner voice is located, yourself. Alright? So far I've introduced you gently, carefully, painlessly, I hope, into the brain cortex. So now that you know that there are certain areas there on one side of the brain, and you know you have two halves of the brain, then you need some way of communicating again between among these different portions. They must talk amongst themselves, and then this part of the brain must talk with the other side. So you need interconnections. So here is a brain cut across the middle, or a cross section, just to emphasize connections of white matter connecting the two cerebral hemispheres. You have one large humongous one here, and you have smaller ones not visible on this particular slice, which helps communicate from this temporal part of your brain to this other temporal part of the brain. And you need to connect. Let's say what you saw is only half of the picture. You need what you see on this side to make a complete picture. So this is your corpus callosum. So based on this animated GIF, based on a diffusion tractography, diffusion tensor tractography, or DTT for short. So this is a certain technological advancement which helps highlight those white matter in your brains. And the easiest one to highlight is the largest one, which is the corpus callosum, right here connecting the two hemispheres together. So by now, through social media, from learning from books and other things you may have encountered before, you know that there is a dominant half of your cerebral hemisphere. 90% of everyone, it is on the left side for some reason. That's why 90% of people are usually right-handed. And even left-handed people will also have a certain percentage which are also left hemisphere dominant. So this is a slice, which is what we call a eggshell cut. So if you cut a brain horizontally, you get this kind of oriented slice. On this eggshell slice, so this is the left and this is the right, with tractography and or with dissection of gross brains, the fibers are particularly much thicker here in the left hemisphere, which correspond to those language areas we showed earlier in the front part and in the temporal part of the brain. And since that is dominant, which makes the non-dominant a brain, how should we call it? No read, no write, illiterate. So the right non-dominant brain is not very knowledgeable of what's going on. So it depends on your language areas here on the dominant hemisphere for you to make sense of what's going on. So how do we know this? So they say neurology or neuroscience is learned stroke by stroke. And it is from the strokes, and a minority of the time from brain tumors or from trauma, that we found that if a lesion, so a lesion is anything that damages the brain. So a lesion is a damaged part of anything. So a lesion, no, a lesion, Lesion, here would disconnect your literate brain from your illiterate brain. So from then on, if this was damaged, then the person could not speak, could not talk, could not understand what's going on. But if the lesion was here on the right, they could still understand what was going on. They could understand words, they could speak. So by then the neurologist deduced that the left hemisphere is usually the dominant hemisphere. And in particular, those who had their corpus callosum cut, and I will emphasize this again when we revisit this after a few weeks, it's like they're two different people already. So whatever this half of the brain is doing, the right half of the brain seems to be undoing. Like if they're asked to button their shirts, they would button it, but the other hand would seem to be unbuttoning the shirt. So stalemate, no? Depending on which is more active. Right? So the emphasis of this slide, I diverge so much, is that the left side of the brain has a lot more thicker fibers because of the language dominance on this side. So I intentionally cut my lectures into portions. So it is 10:57. So if you have any questions for me at this point, you can ask it now, or you can ask it later. That's all right. Okay, so checking the chat. Okay. Can you repeat which area of the brain is responsible for phantom pain? So just to repeat, so we go back here again. Right, this area of the brain that feels has assignments. So more or less, this is the leg area. More or less, this bump here is for the arms, and more or less, this area here is for the brain, for the head and face, especially the face area. No, so there may be, if the person lost an arm in adult life, meaning they were born with an arm but they lost it, they can still feel it, like it's still there, even if they've lost it, because of the neurons that are still here, assigned for the arm and the hand. So this did not lose its function, it's just that they were orphaned. So this gives rise to your phantom limb phenomenon. Partly, it's called plasticity of the brain, because until they're assigned, they will be reassigned to the leg or to the face, but they're still there, no? But sometimes they still remember what they used to do before. Hence, some people and until a certain amount of time passes, we'll still feel that their arm is there, but it's actually cut already. So with the passage of time, the assignments will change. So those neurons will now be reassigned by the one next, but area next to them. So the ones closest to the face will assume more sensitive face sensation, whereas the legs will feel more sensitive. This is partly how blind people are able to get around as well as we do, because certain parts of their brain, the feeling parts, have taken over what was never developed here in the visual parts of the brain. So the brain is plastic. So from day one, I'm already mentioning it, and we will hear that on the last day of OS 202. All right, I hope I answered that question. Okay, so we go to the part two of three parts.
Doc, we have one question lang po
Yes,
from
go
the
ahead.
class.
Yes.
Go ahead lang. Yes, yes,
Oh,
KDB.
okay. Doc, I wanted to ask if there was a particular reason why the occipital, like the visual part of the brain, is so far from the eyes, but then the hearing part is so close to the ears.
Well, it's a matter of development. So, uh, if you want to count percentage of the brain assignments, a large proportion is actually assigned for the motor part. As you see in this screen, the front part, all of that is dedicated to movement. What remains is now divided between sensation of pain, of touch, of hearing, and of vision. So it just so happens we are able to move around even in the dark. No? So if you go back to the ancient times where there was no electricity yet, you are still able to hunt by starlight or moonlight because of our sense of direction. No, using the stars, our sense of hearing was also keen. There were no headphones yet, no earphones yet at the time. So it's located here just by the bulk of development of this motor part of the brain here. And it got squished back here because we had to make sense. No? So we were not just dumb animals, we were intelligent animals. We had to make sense, and we had language to contend with as well. So we had to do with language, and we had to do with memories. So our memories are a lot better than previous stages in evolution. So the association cortices actually occupy a large proportion of this parietal area here, no? As we will go through later. I hope I answered your question. It's really it's like you're in a room and there are more intermed than psych majors, so the psych majors are pushed to the back, and or there are more PTOTs in the batch, or a lot of bio majors occupying the space. No, so it's really which are the dominant assigned areas in the brain or in your class, which are the most dominant pre-med groups. It's really a matter of numbers. No other
Oh,
special reason. Yeah.
thank you, Doc.
Okay. Okay. Part two. If you're still okay, it is 11 o'clock. Okay. So again, definition of terms. No? When you see this word on the screen, that's why I intentionally did not say this word when I was lecturing the first part. No? So see what when you see this word, how do you pronounce it? So it now I notice it differs among different schools. No? Which med school you went to. Okay, so since we're in UP, and we are also based on primary sources, so if you go back to your primary sources of language, so this is a Latin term. So it's gyrus. No? So but some schools, some graduates would call it gyrus. So which is which? So your guide for which is correct, it's always the cat who's correct. No, so it's gyrus, not gyrus. So maybe I shouldn't catch you in the future saying gyrus, ha? Kasi it's wrong. No, it's gyrus. Then So gyrus is, or gyri, no, the correct plural term is gyri. These are those ridges that we saw on the uncut brain specimens I flashed earlier. So some are deep, some are shallow. So it can be, when it's shallow, and I'm sure you've heard the term already in OS 203 and 204, though you have this word. So that's another term we need to make sure we pronounce correctly, this word over here. I didn't pronounce it because I want to see what is in your heads. No? But generally, the deepest ones are what we call the fissures. And less deep ones we call this. No? So go back to the cat. No? Some would say sulci. I think 98% of everyone who reads this word will pronounce it as sulci. And we will not be faulted for that. No? So really have to go back to the primary sources. It's really pronounced as sulci. And we see that when we're describing something on imaging like CT scan or MRI, when we talk about the sulci, if they are obliterated or if they are absent, we say there's sulcal effacement, meaning nawala yung sulci. So sulci, it's not sulci, no? That's wrong. So it's sulci. So let's get that straight, no? From the previous batches and your batch as well. No? Sulci. So since I started teaching, I have always used this picture. This is a chocolate, a bar of chocolate with ridges. So the ridges that you see here elevated, those are the gyri. The ridges, the deep lines here are the sulci or sulcus, sulci, gyrus, gyri. Okay, just for emphasis. Okay, this CAPTCHA, where is the ridge? So flashbacks from your 203 SGD. So that is the bicipital groove or sulcus. So everything else are gyri or ridges over here in these pictures here. So just definition of terms, so gyri are those elevated structures that you see nicely over there. And the sulci or sulcus are the deep things over there. Whereas this very deep thing here, this deep groove is a fissure, a large deep sulcus. Right? So here is your brain. This is the front part of the brain, and a large proportion dedicated to movement and planning, and more or less your direction in life over here. So your attention spans are located here. So what does it look like? So for those of you who have not seen a brain before, so this is a brain seen from the front. So you see ridges, you see valleys, mountains and valleys here. So very similar to a intestine of a chicken. So very similar to isaw, if you want to look at it that way. So why do I flash this isaw? No? Not to promote Manglari, but to promote the fact that there are gyri. The direction of a gyri helps you from getting lost, no, in the brain. It looks like a mess. No? So, but this is a gyrus. It's just curled. No? It's curled, but it goes in a direction from anterior to posterior, followed by another one here, the gyrus that goes from anterior to posterior, and the last one here where we found the speech areas earlier is also directed from anterior to posterior. Now you have these three pairs of gyri here in the front. So this is the frontal lobe of the brain. Now, if you look at the brain from below, so we see here also another pair of gyri which are oriented from anterior to posterior. So what I'm showing you are constants. So for gyri here in front, in the frontal lobe, are usually directed antero-posteriorly. So you have a superior, a middle, and an inferior, the pairs of gyri here. And here at the base of the brain, you have this very straight looking gyrus here. So very convenient because the anatomists just called it the straight gyrus, or the so-called gyrus rectus, which happens to be a landmark for one of the 12 cranial nerves that you will encounter here. So this happens to be the cranial nerve that facilitates your sense of smell. This is also attacked by your SARS-CoV-2 virus. This is the olfactory nerve, which is the only cranial nerve found here on the cerebral hemisphere. Literally on the cerebral hemisphere. There is a cranial nerve 0, but we'll get into that tomorrow. Alright? So everything else around this area, so by convenience, since this was taken from a cadaver, this part of the frontal lobe is right above the orbits. So hence, for lack of a better term, the anatomists called it, or called them, the orbital gyri, alongside those straight gyri of the frontal lobe. Now, the temporal lobe that we saw earlier, this is how it looks like when you're looking at it from the bottom. So these are located above your temples, hence they were called the temporal lobes, one on each side. Then here behind it, or below the temporal lobes, is the brainstem and the cerebellum. So I'll be lecturing to you on the brainstem. Dr. Baticolon will lecture to you on the cerebellum. And Dr. Baticolon will also lecture to you on this piece of brain here, the diencephalon. So to recap, front part of the brain, temple part of the brain. So frontal, temporal. So this is just for emphasis, to remember that configuration when you're looking at the brain from below. So it's like this guy waving here, with both hands. So now we go back to the front. So this is the front part of the brain, and we see, so this is a different specimen, but we notice this gyrus going from front to back, another one front to back, and the most inferior one going front to back. So remembering these three gyri will help us from getting lost when we look at the brain from a different angle pretty soon. This one. So again, a different brain, and then it's still wrapped up in its pia mater and some brain tissue scattered all over it. So how do you make sense of this? So for one, we need to peel off this pia mater. So the pia mater, as you can see, contains all those blood vessels which go against what you see in the atlas. So the atlas pictures are already cleaned off their pia mater, so they look so nice. So this is the natural brain as we see it. So we have to peel this off so we can see those three pairs of gyri in front, so that everything else is something else. So this is the front part of the brain, and this is the occipital part of the brain. So we stop here and we try to figure out a pattern recognition. So which part of the brain is rounder and more bulb-like? This front part or this occipital part? So just for memorization's sake, ito matulis ang puwet. So the matulis ang puwet part, that's your occipital. So the frontal lobe will never be this sharply shaped, whereas the frontal lobe will always be light bulb. If you think of a light bulb, that's how the brain is described at times. So the bulb-like frontal lobes in the matulis na puwet part ng occipital. Okay, so that's frontal, that's occipital, and this area around here is parietal, and here below is the temporal. So we need to peel off that pia mater to see a landmark, something that is often seen and commonly seen across all different brains. So here we're looking at the brain from the back. So again, the clue here is that cerebellum, a pair of cerebellar hemispheres below it, but they will not always be there. So our only clue would be to look at this part, uh, looking at it from the lateral view. So looking at it from this point, very hard to distinguish if it is a occipital or a frontal lobe, no, from this angle. So you need to look at it from the side to see if matulis, no, matulis siya. So this is very sharp. No, this is actually the occipital lobes over here. And it seems to be sticking out a tongue at you. No? So we'll get to that in a while. That there's a tongue part of the occipital lobe over there. So another brain on the right side, the pia mater has been removed, but this brain has been discolored by time. It has been lying on its head the whole time for a year in formaldehyde. But we look for patterns. So we look here first in the front. We need to see 3 pairs of gyri oriented antero posteriorly. We follow it until it stops. There, it stops here. Here, the middle frontal gyrus, curly, but it ends here as well. And then this inferior frontal lobe, which for some reason has a very large triangular part here, for a reason. So that is actually the part of your inferior frontal gyrus that is in charge of programming your speech. More on that later, since we're just describing for now the 3 pairs of anterolaterally oriented gyri. So they all end up here. The inferior frontal one ended up here, the middle one ended here, and the superior frontal one ended here, which gives you the final gyrus of the frontal lobe, which is not oriented in the same way. This differently oriented gyrus, which seems to go from vertex to ear, is known as your precentral gyrus. This is where most of the motor neurons are located. This is the primary motor cortex. Again, this is not the landmark that we were looking for, but we know that this is the only gyrus in the frontal part of the brain which is not directed towards the frontal pole over here. It is oriented towards the ear. And it ends up in this very deep groove over here, the lateral fissure, since that's a very deep sulcus. So in the beginning, they're all up for grabs in terms of naming. So the first one to get to name it was Sylvius. So it is named after him. The lateral fissure of Sylvius, or the Sylvian fissure, which conveniently separates the frontal part of the brain from the temporal part of the brain. So that separation that we see here is not artificial, it is real. That is the Sylvian fissure. And you see this important artery peeking out from inside. So more on that important artery next on Friday. So we're looking at the temporal lobe here, very similar to the front. The gyri are oriented antero-posteriorly. So you have a superior temporal gyrus here, you have a middle temporal gyrus here, and the most inferior one, same way, no? So directed antero-posteriorly. So odd man out, the only one that is directed from vertex to ear is actually this one, no? The precentral gyrus of the frontal lobe. It gets more confusing behind it. So they're not as clear cut as this particular gyrus here. So back to the front. So that is a dura mater, which looks like a glove. So that's the dura mater meninges of the cerebral hemisphere. going inside this interhemispheric fissure. So now this one, so this is nice. This is taken from the Washington University in the US. So no cuts, very nicely dissected, no more pia matter. Here in the front, on the top part of the brain. So as mentioned, you have to take away the pia mater to get a better look at the sulci, which will guide you to where is the front and where is the back, assuming it has been misshapen from a long time in the jar. No? The roundness of the frontal lobe may not be that clear cut anymore, and the sharpness of the occipital lobes will not be that distinct as well. So what is our clue? So we take away first the pia mater of this cerebral hemisphere. So while we're here, these are the Pacchionian granulations, which help absorb the cerebrospinal fluid. Right? So this is just emphasizing that deep fissure. So we'll skip this slide. Back to this part of the brain. So this is the bottom of the brain, and we've cut away the brainstem. We've cut away the cerebellar hemispheres. So now we see a concept which is meant to shake the foundations of your neuroanatomy. In this particular view of the brain, you can see that the temporal lobe is actually one with the occipital lobe back here, telling you this is a construct. There is no temporal lobe, there is no occipital lobe, they're just one big lobe here. So which is why what I emphasize is actually function. So this temporal lobe here houses something important which you have been using the entire time to survive 204, 203, and biochem. The memory center for short-term memory is actually housed inside here. And to make it make sense, whatever you try to memorize, of course you have seen. So you saw it with your eyes, you heard it with your ears, and you stored it initially here in your short-term memory area. Ideally, it should go into your long-term memories around here, but somehow they all were washed away, no, with the tears of the short-term memory. So just emphasizing temporal lobe and occipital lobe are actually one within the same structure. That's why when we look at the base of the brain, you actually see longitudinal gyri directed again from front to back. You have one medial one here, this medial occipitotemporal gyrus, and a thicker lateral occipitotemporal gyrus. So these are important for vision, for actually recognizing certain words. So word recognition areas are found here for a reason. This is a association area. Association area. It makes sense of what you heard, what you saw, and what you remembered here in this visual area of the brain. So these are actually one and the same. No? So what you saw earlier down here connects the temporal lobe with your occipital lobe back here. Which brings us back to this side. So what we've been introduced to so far, the front part of the brain, the temporal part of the brain. So frontal, temporal. For now you recognize the frontal lobe is over here, the temporal lobe is over here. They are separated by that deep fissure over here, the Sylvian fissure. So around this area is that around thing, no? Parietal means around this area. And then the sharper occipital pole over here. So poles, frontal pole, very round light bulb, and the smaller light bulb over here, the temporal pole, and the sharp occipital pole over here. So now we wanted to peel away that PA matter to look for a constant across all brains, regardless of age and size. There will always be a central sulcus of Rolando. So how do we recognize that central sulcus of Rolando? First, by mentally subtracting the superior frontal gyrus here. So you see anterior posterior, it stops here. Then you see that precentral gyrus here. Behind that precentral gyrus is a very distinct, constant groove that goes from the vertex, makes a loop here, and that we will get to when we go into details about the cerebral cortex, then goes down towards the sylvian fissure. So it follows this precentral gyrus. So remember, it's all artificial constructs because if you look at this right side here, it seems to be continuous with the superior frontal gyrus here. They seem to merge. No, there's no separation. So the sulcus in front of that precentral gyrus is named the precentral sulcus. So just because it's there, it's given a name. Significance? None whatsoever. So we just need to know this one. So this is where your motor neuron controllers are, the precentral gyrus or the primary motor cortex. And behind it, what seems to form an omega shaped curve there, that's your central sulcus. Again, that omega shape is not constant. Even in this brain, on the left side, it's not really omega shaped. But on this side, it is omega shaped. So that central sulcus goes down, dives deep down. It almost touches on the sylvian fissure. So your atlases might be inaccurate in that they seem to end in the sylvian fissure. Usually it doesn't, which tells you something about the gyrus behind it. So that was the sensory cortex. This is the motor cortex. Why are they one and the same structure when you get down here? Especially if you peek in between the hemispheres behind here. They are actually one and the same structure, which tells you how very closely related your motion and your sensation are in performing your daily activities. So here, unlabeled, colored. So where would the central sulcus be here? Because the only thing that you would be confident in pointing out would be the sylvian fissure here. So, first clue, is there a superior frontal gyrus which ends up somewhere? No? So, going from here, going back here, it seems to end here. And this middle frontal gyrus, which seems to be doubled, ends here. And that, sorry, let's hide that first. No, the inferior frontal gyrus ends up here. So we have this particular gyrus, which is oriented from vertex to ear. So this is the precentral gyrus. Therefore, the central sulcus would be the consistent deep line here. So again, this is artificial. It doesn't really end in the sylvian fissure. So my yellow tracing also doesn't end there. There's a gap there, which tells you that this post-central gyrus over here is actually one in the same structure as this pre-central gyrus over here. The motor and the sensory cortex are in the same area, divided artificially by that central sulcus of Rolando. It's really divergence of the differentiation of the neurons as they multiplied and multiplied in number, spreading like if you remember your earth science in the deep sea floor, with the continental drift theory. So the sea floor is spreading on opposite ends, no, going different directions, and that formed your frontal and your parietal. So the cells multiplied and pushed everything to the back here. So here on the opposite side, so again, mental exercise. go for what is given. So the sylvian fissure is given. It's this very deep fissure here. Then you see all these different lines here. So very confusing. Which one is the central sulcus? So you use logic. Logic tells you that there are three gyri here in front, which are directed frontal to occipital. So you follow the frontal gyrus back here until it reaches this particular gyrus here that travels from the vertex of the head going down towards the ear. And bearing in mind that that central sulcus doesn't really end up in the fissure but just above it, then more or less, if you chose this line as the central sulcus, you are correct. Using a step-by-step Bobo-friendly approach. So we assume ourselves as ignorant in the beginning. We don't know anything, therefore we are easier to teach, and it's easier to learn, and we don't have any biases in our minds that tells us we know everything. Right. So therefore, the central sulcus help define what is frontal from what is parietal, because the parietal lobe is notoriously devoid of any clear-cut boundaries other than that central sulcus. As you remember, all of these lobes are actually artificial constructs. They do not actually exist. We only know of areas. So that central sulcus divides the frontal from the parietal over here, and that sylvian fissure separates the frontal from the temporal over here. Therefore, by mental subtraction, this area which is not frontal and not temporal is your parietal lobe. And even for me, it's really hard for me to distinguish what are the separate gyri found here. So what are the tips that we can use so that we find our way without needing a very high IQ. So first, the central sulcus. The constant is behind every, that's the precentral sulcus in front of the precentral gyrus. So already outlined for you here, the central sulcus, meaning what's in front is frontal, what is behind is parietal. Okay, so precentral gyrus in front. And then there's always a precentral sulcus there which is never complete. And then behind it, behind that precentral sulcus and in front of the central sulcus is the precentral gyrus. The sylvian fissure helps define where the precentral gyrus ends. So frontal in front, parietal behind that central sulcus, and then temporal lobe beneath that sylvian fissure. It's just a matter of this one, and even the books will tell you what separates the parietal lobe from the occipital lobe is actually imaginary if you're looking at it from the outside. So here, what we know is that this is temporal. Okay, we follow the superior frontal gyrus to where it ends here into this gyrus, which is going downwards towards the sylvian fissure. Same thing here. Same thing here. So mental exercise locating the central sulcus will help you locate everything else. So two different sulci. The central sulcus and the sylvian fissure are your friends. They will help you when you're lost. Here, with this nicely dissected specimen, you know that you're looking at the frontal lobe, and you're looking at that superior frontal gyrus going from front to back. Frontal, middle, and inferior, with that straight gyrus underneath. Okay, this is the ventral surface again. I should not repeat myself. So, superior frontal gyrus, it has its own sulcus, which you do not need to remember. You have that middle frontal gyrus in its own sulcus, which you do not need to remember, since there are only three lobes here, gyri here. Then two incomplete sulci will separate them. The superior frontal sulcus and the inferior frontal sulcus, to separate the middle frontal gyrus from the inferior frontal gyrus. Again, not something you'd want to waste time on. So that's your inferior frontal gyrus. So just a schematic in terms of orientation. The three frontal gyri are oriented front to back, stopped by a precentral gyrus which goes from vertex to ear. Right? So drawing some attention now to the inferior frontal gyrus, a term appears, operculum. So what does operculum mean? Operculum just means eyelid. So this flap of frontal lobe here, and a flap of this temporal lobe here, and a flap from the parietal lobe, you can actually uh, push aside with your finger to see something underneath. More on that later. There is a lobe hidden inside, so a brain within a brain inside. More on that later. So this inferior frontal gyrus, so that operculum contribution is known as the opercular part, or the pars or opercularis. Why are we naming it that way? It's a bookmark for us because they correspond to very important language functions. So the opercular part over here, so what opercular means, it's just the eyelid over the sylvian fissure. That helps you remember it. So this opercular part is then behind a triangular part. So again, this is a stretch of your imagination. For some reason, they want to call it the pars triangularis, or a triangular part of the inferior frontal gyrus. It doesn't really look that way to me, but the name has to stick. No, there's no other name for it. The pars triangularis. And then the remainder, which is actually grouped together with our other orbital gyri beneath, is the orbital part, the pars orbitalis. So that is your inferior frontal gyrus. The reason why they are so excited about this pars triangularis, because its apex over here is actually a landmark for the neurosurgeons. So when they see this apex over here, it tells you, oh, yeah, we're near the sylvian fissure. It always points at the sylvian fissure. Alright, so just going through this very fast. The precentral sulcus, superior frontal, inferior frontal. Again, these are just lines. These are just constructs, not very important. What's more important are the gyri here in front, which helps you find the, well, for one, the anterior sylvan point for neurosurgeons or future neurosurgeons. Okay, the pars triangularis, pars opercularis, closest to the precentral gyrus, and the pars orbitalis, which is closer to the orbital gyri beneath. So, sorry, that's a typo. That's orbitalis. Right, and depending on how talkative you are, the pars triangularis, again, if neurons will be assigned to how much you use them. So pars triangularis can be sharper or rounder depending on the person. So again, it doesn't always look triangular, if that helps. No? Right, back to the top, the central sulcus, the precentral gyrus in front, the inconsistent precentral sulcus in front of that precentral gyrus. Again, don't kill yourselves over the frontal sulci. Just remember the superior frontal gyrus, which helps you find this precentral gyrus. And below, the straight gyrus with the olfactory nerve inside its sulcus, and the orbital gyri. And lateral to that will be the pars orbitalis of the inferior frontal lobe. Right? More and more colored pictures coming up. So straight gyrus, orbital gyrus or gyri, uh, a view from the front, the superior frontal, middle frontal, inferior frontal gyrus. So behind them, the precentral gyrus. Beneath those, the orbital gyri. The straight gyrus completes your frontal lobe. Now, about the parietal. So behind that central sulcus, again, it becomes very vague. No? So your only landmark would be the central sulcus and the sylvian fissure. This helps you triangulate that you're looking at the post-central gyrus, which contains your sensory cortex. So it would have also its own inconsistent post-central sulcus behind it. Again, don't lose your minds looking for that. Looking at it from the top. So the precentral gyrus behind the central sulcus. Again, it works when you have colored pencils or crayons to color the brain pictures so that it helps you from getting lost. So you have those precentral gyrus and postcentral gyrus. If you look at it, it's not really clear cut. Sometimes it forks and forms two gyri looking things over here, or it loops inside. They don't even look the same when you compare left and right. What is constant is the central sulcus. So it really depends how much neurons were dedicated for a sensation in this particular person's brain. Alright, so that parietal part of the brain, that is what we call the superior parietal lobule. Everything behind that postcentral gyrus. So importance, the visual cortex is just behind. The somatosensory cortex is in front. Deduction, it connects what you see with what you sense. So those of you who like to catch frisbees in midair or catch balls or swat volleyballs, value eye-hand coordination, which is located in this area in your superior parietal lobules. So parietal lobe contains postcentral gyrus and two lobules. The superior one up here and an inferior one very close to the sylvian fissure. So we have landmarks for this inferior parietal lobule. So more on this intraparietal sulcus in a while. So its location also gives us an idea of what it does. It is located, this particular sulcus, which is quite consistent in brains, can be seen separating that superior parietal lobule from the inferior parietal lobule lateral to it. So this is important for your visual attention spans. If the frontal lobe is for your attention itself, directing where your eyes will look is located here in the intraparietal sulcus. Now, I will introduce to you an area here in front later on, which is actually in charge of your eyeballs. So it makes sense. Your eyeballs are directed by this part of your brain in the superior frontal gyrus and works well with this area of brain here near this deep sulcus, the intraparietal sulcus. So visual attention and where your eyeballs actually are resting on any particular time. So your visual. So those of you who do have a problem with keeping your eyes on one object for a certain amount of time, just understand yourselves better that maybe your frontal eye fields here and your visual attention areas here are overstimulated, so they cannot rest on any particular area in front of your eyes, front of your face. So importance of the IPS, or the intraparietal sulcus. So mentally subtracting the parietal lobe minus your post-central gyrus minus that in the superior parietal lobule equals inferior parietal lobule. Now, what do we use as our guide this time? Of course, we have the central sulcus here. We have the sylvian fissure here. So, where the sylvian fissure ends and behind the postcentral gyrus is your one half of your inferior parietal lobule. That is the supramarginal gyrus. Why is it called the supramarginal gyrus? I also do not know. If it were up to me, I would call it the gyrus above the sylvian fissure in the parietal lobe. But then they don't want to call it that, so let's just stick with supramarginal gyrus. Think of it as the part of your brain that provides your inner voice. Although some social media posts would say some people do not have a inner voice in their heads talking. No? Just one, not multiple voices talking at the same time. Just one voice. Your own personal voice is here in your dominant hemisphere's supramarginal gyrus. Okay, so that's one way of remembering it. So your inner voice. The other part of that inferior parietal lobule, which is the most important one, which makes sense of everything that you're experiencing so far, is the so-called angular gyrus. Now, our landmark for that is to use this the gyrus of the temporal lobe, the superior temporal gyrus, has its sulcus. No, it's not complete, as you can see here. It breaks into two. But if you follow it posteriorly, that the superior temporal sulcus will end up in this angular gyrus. So more on that when I go into details later in the following weeks. That is your angular gyrus. It makes sense of everything. Okay, so supramarginal gyrus, our landmark is the sylvian fissure. Whereas the superior temporal gyrus helps us find, a superior temporal sulcus helps us find the angular gyrus. So at this point, I may be talking a lot about it now, but you can just park it in an area of your brain and remember where you parked it. We will revisit this later on due to its importance. Alright, so subtracting again, if you subtract everything else from the parietal, that leaves you everything else here at the back of the brain. The posterior cerebrum contains your occipital lobe. So I mentioned over here would be an artificial boundary, but as you peek in between hemispheres, there's actually a very deep fissure there that separates your parietal from your occipital, the so-called parieto-occipital sulcus, or fissure, more correctly, because of it's a very deep fissure. Alright, just rounding up these slides, just coloring the gyri as we encounter them. Superior parietal lobule, the intraparietal sulcus, which is constant and deep. So whatever is important is usually deep anyway. So something to remember. If it's very shallow like this, maybe it's not that important. So inferior parietal lobule is important because it's important for language, making sense of language. And here, as you draw closer to the midline, is a very deep fissure, the parieto-occipital fissure, which defines now what is left of your brain, which is your occipital lobe. So you can imagine your visual connections have to travel very far from the eyeballs here in front to get to here. So those fibers really have to go several what do you call this, stopovers to get to here. Right, just giving the configuration for the parietal. What is constant a vertex to ear oriented post central gyrus of varying shapes, a superior parietal lobule separated from the inferior parietal lobule, very very deep sulcus here, the intraparietal sulcus, and a very indistinct inferior parietal lobule, which we will need the help of the sylvian fissure and the superior temporal sulcus to find the two different gyri, the angular gyrus and the supramarginal gyrus here by the sylvian fissure, and the angular gyrus of what remains of that inferior parietal lobule. So that's the schematic over here. The colors will persist as I go into the functions in the succeeding weeks. But for now, I'm just introducing to you the different important gyri. So more or less, you know where the parietal lobe is, it's around here. More or less, you know that this is the frontal lobe, and more or less, you know that this is the temporal lobe. And with a bit of going back and forth in the slides or in the recording, if you're listening to this at a different time, the gyri here behind, the sulcus here, the sylvian fissure, and this sulcus here that you follow to the end helps you locate important parts of that parietal lobe in the inferior parietal lobule. So again, baby steps. I do not expect you to remember everything I just said. Maybe most of it is a blur, but that's okay. That's how the brain works. You really need to get beyond that short-term memory area here. Right. Okay, so you can actually click through this in your copies of the PDF to get the different areas to form your own personal coloring book of the brain. Just clicking through it so that you see how you study anatomy is bit by bit by bit, using landmarks and other landmarks. Alright, I'll be clicking through this since we already mentioned this earlier, and complete the coloring book. And you can make your own. Just get a black and white picture from Washington University and use your own. Either you print it out and color it, or you color it with your devices. Now going down to the bottom to revisit this construct known as the temporal lobe and occipital lobe. So we followed it from the lateral surface. We knew that there is a inferior temporal gyrus over here. Again, once you get to the atlas and you compare it with the real brain, this is the confusing part. Alright? So they are not the same. But what is constant here when you look at the base of the temporal lobe, where it continues on as the occipital lobe, there will be some grooves there. And the grooves will not be as perfect as the picture that you see on screen. They may be like this one. They're not complete. They're cut into 2 or 3 different sulci. But regardless of how complete they are or how nice they look on the atlas versus how blurred they look on the actual brain, you know that there will be a pair of major grooves or sulci at the bottom of this brain, which connect the temporal with the occipital, and we call these occipitotemporal sulci. Now, without looking at the names, we just look at the brains. We look at this constants. No? So once you get to this bottom surface of the temporal lobe where it becomes occipital, you see this tongue-like structure here. Okay, it's tongue-like. It seems to protrude towards the midline here. Okay, so I'll just be clicking through this. I'll just fast forward to this one here. The one with the tongue happens, well, for lack of a better term, someone called it the lingual gyrus, which is okay if you know where you are. But if you are lost, then we go technical. There is a pair of gyri here at the bottom. You have the medial one, which is the medial occipital-temporal gyrus, or MOG if you want to use abbreviations, and a lateral uh, occipital-temporal gyrus, or LOG, or LOTG. Okay. Uh, the reason they're called that is one, this is the tongue-like gyrus, hence lingual gyrus. But why did they call the lateral one fusiform? Again, this one needs some research. No? Fusiform, it just means the shape. The shape of the gyrus is like triangular. But don't confuse yourselves. Just remember, it is the bigger one of the two pairs of gyri that we look here, no? Looking at the base of the temporal and occipital lobes. So we call it fusiform. It helps us remember something, no? Fusiform. Uh, face. No? This is actually the part of your brains that recognizes faces. Fusiform. So if you have something happening here that destroys it and it spares everything else, that person no longer recognizes faces. And there's a term for that that I will not confuse you with right now. The inability to recognize faces is if you damage this faciform gyrus, or the better known as the lateral occipitotemporal gyrus. So about this sulci, maybe not so important for us because they're very inconsistent. So it's just there to name things. So between the fusiform and the lingual gyrus is the collateral sulcus for some reason. Alright? And since all of you have been seeing are actually artificial constructs, this is the part of your brain that is in charge of vision and remembering what you saw. So let's just call this visual cortex. Damage that, you don't see anyone anymore. You don't recognize anything or anyone anymore. So just to complete the picture, the thing that was left behind here that I was saying houses your short-term memory, houses the hippocampus. So hippocampus is the part of your brain that remembers and forgets after every exam or after any traumatic event in med school. Okay, it houses the hippocampus. Therefore, it is called the parahippocampal gyrus, or the gyrus around the hippocampus. It is the most medial part of your temporal lobe, which, as we know, is a construct because it's actually one and the same structure with the occipital lobe over here. So, for schematic purposes, looking at the base of the temporal lobe, you have a fusiform gyrus and a lingual gyrus, and to complete the temporal lobe would be the parahippocampal gyrus over here. And peeking laterally is the inferior temporal gyrus, which we saw from the lateral surface of the brain. Right? So, again, we don't waste our time remembering this sulci. We just remember areas here, since the sulci can be quite confusing and inconsistent across atlases that you're looking at. Okay, so that's the inferior temporal gyrus, separated from the fusiform gyrus by a sulcus there. So that is your fusiform gyrus, or the LOG, and the MOG, also known as the lingual gyrus. And then the parahippocampal gyrus, which contains a very knob-shaped structure here, which can be the killer in our patients. So this tiny but terrible structure can really press on the brainstem and lead to death. That is the whole point of teaching you this piece by piece, so that in the future you would recognize when this uncus of the temporal lobe is already pressing down on the brainstem, we're already reaching the point of no return for our patients. So we really need to teach this as early as first year med school, so that you'll eventually realize the importance of this structure compressing on this structure you'll be introduced to tomorrow, the midbrain, because it is fatal. So you don't want this temporal lobe to go where it doesn't belong and uh, compress on this brainstem here. Alright, I hope you're still with me. We're gonna finish off the lecture by going on the insides now. So this is the parieto-occipital fissure, which, as you can see with this chopstick, is easy to delineate when you're looking at the medial surface of the brain without all the pia matter. No, it's all been removed. So it's a parieto-occipital sulcus or fissure which separates the parietal from the temporal occipital area of the brain here, or the visual cortex. So parieto-occipital fissure separating the parietal from the occipital. So this particular fissure here is constant, and it is a very important fissure because this area is the river, and the river banks is the so-called primary visual cortex on the banks of this sulcus here. And just to refresh your short-term memories, this structure here beneath that calcarine fissure is actually your lingual gyrus from the temporal lobe. Right? So, with these two grooves here, the parieto-occipital fissure and the calcarine fissure here, which forms the banks of the occipital or the visual cortex, this wedge of tissue here, a term is very similar to the term you saw in the hand skeleton, cuneus. Cuneus means wedge. So the wedge here inside your brain is your occipital lobe, the cuneus. So in front of it, for lack of a better term, in front of the parieto-occipital fissure, so this is parietal, we just called it precuneus, so the area in front of the cuneus. Importance, this is just the inner surface of that eye to hand coordination area, this precuneus here. Whereas this one beneath here is actually part of your visual cortex, the lingual gyrus of the temporal lobe, or the occipitotemporal area of the brain. And then a favorite portion of the brain for mine, which demonstrates why those frontal, parietal, temporal, occipital are actually artificial terms, is this gyrus here above the corpus callosum. So it's my favorite gyrus because this is what makes us who we are. Our decisions, how we feel, our empathy towards other people, our humanity is residing inside this particular gyrus, the cingulate gyrus. So cingulate from the term sing, ring. No, it forms a ring around the corpus callosum. Okay, so all the single ladies put a ring on it is actually derived from neuroanatomy. So Beyonce. So cingulate gyrus forms a ring around this area here where the corpus callosum is. So this structure up here, if you actually followed it from the lateral surface, these are actually the pre and post central gyrus combined. So this is since it's a combination of gyri, this is a lobule. So it's in the where the central sulcus is. So we call it the para-central, or the area around the central sulcus lobule. So what does this image tell us? This is where your bladder functions reside. So beyond the leg and the feet area are now the genital and the bladder areas represented here inside your paracentral lobule. And then the structure here, which I showed you earlier, the uncus from the parahippocampal gyrus. So the uncus, again, emphasized for importance in terms of life versus death inside that parahippocampal gyrus over here. Okay, so now we have this brain in front of us. So using coloring book techniques, using what we can see, what is constant, you see that parietal occipital fissure over there. You have the corpus callosum over here, with the brainstem beneath that in the diencephalon. So, but for now, we're concentrating on this tissue up here. So that's the central sulcus, which ends up in this paracentral lobule. That's your parietal occipital sulcus, separating the parietal from the occipital. And within the occipital lobe, you have that calcarine fissure, where the visual cortex resides. Other relatively less important sulci, which just helps form boundaries for us to delineate the areas. And then above that cingulate gyrus, its own personal sulcus, which travels from front to parietal to occipital. You have the areas formed by those sulci, the cuneus wedge over here, the area in front of the wedge, the important cingulate gyrus, and the paracentral lobule up here. That's your corpus callosum, which connects your two hemispheres. Okay, and a smaller connection down here, which I'll get into detail in a while. It is now 12:06. Those of you who want to eat lunch can go ahead already. I am recording this for you if you wish to exit the Zoom meeting. And then connection, which you will get to know later on. This is the connection from your hippocampus to everything else, the so-called fornix. Again, we're just introducing to you these terms, these structures. You're not expected to remember it all at once. Not from the first lecture, not from the second viewing of the recording, but maybe as we go along through the module. Okay, I was mentioning the brain within the brain, hidden by the operculum of the frontal, temporal, and parietal lobes. That brain within the brain is your inception. That is your insula, covered by those eyelids. So the insula is a piece of brain which contains those gray matter hidden by the development of the telencephalon. So inside the insula is the so-called basal ganglia. So importance, you will get to that pretty soon, but not today. So the insula is the brain within the brain. There's a reason for it being there, why it's there hidden inside. So just to give you a taste, this is what makes you feel intensely about something, or what makes something intense taste intensely good, what tastes intensely disgusting, makes your feelings intensely strong for a person or something. Deep crush, also in here, because it's deep inside, so you have to hide it deep inside. That's the insula. Now the temporal lobes, if you actually removed it from everything else, it actually curls inside. Now, a totally different orientation from everything else that you've seen so far. It is not anterior posterior, it's not from vertex to ear, it's from outside going in. So these are called transverse gyri inside your temporal lobes, where the superior temporal lobe is. It reaches inside towards the insula. So those transverse temporal gyri are called the transverse temporal gyri of Heschel. This is where your hearing cortex resides, like a piano. Higher frequencies are located somewhere, and the lower frequencies are located somewhere. So it's like a piano inside your heads. Even if you're tone deaf, you have a piano inside your heads. Okay, the transverse gyri facial, which are a part of your superior temporal gyri. Okay, this point I'm supposed to show you this website, which I already put the links in your canvas. It's called the Brain Explorer, which will help us with the third part, which is the internal sectioning of the brain in terms of the white matter. So on this website, the fourth panel on the right lower hand corner is your uncut brain. The upper left hand corner is a coronal section, meaning we're cutting it from front to back. This left lower corner is the appearance of the brain as you slice it from vertex to bottom of the head. And then over here is a sagittal appearance of the brain from the midline. So just demonstrating for you as we cut the brain from top to bottom. So I'll use this. You can use a mouse to drag the brain, and then look at this panel over here to look at the eggshell slices. So as we go down from the cortex, going down, you start to see the white matter get together to form a large mass over here. So part 3, I will be going over those parts of the white matter, so very quickly. So as I cut the brain going downwards and reach the ventricles or the CSF pathways, the white matter now forms like a crown, as we will show you later. So that crown around the ventricles or the CSF pathways will gradually narrow down to form this boomerang over here. So more on that boomerang in a while. As I cut deeper and deeper, that white matter has to traverse the gray matter inside of the basal ganglia. So it has to form a boomerang before it descends down into the next lecture tomorrow, which is the brainstem. So the brainstem's over here. So these are fibers coming from the brain, the cerebral cortex, going down towards the brainstem and spinal cord. Okay, so having shown you that cutting, now you more or less will understand part 3. So for those of you who are listening in on a delayed time, or those who are eating lunch as you watch this. So I now go to part 3. So again, this is just introducing you to the white matter inside your brains, which you do not have to remember at this time. So I mentioned those neurons on the top of your cortices will have to send connections downwards. Now this is what they look like if you remove all of the gray matter and just left with the white matter. Right, so you have websites online where you can view this in 3D. So Neuroanatomy Online is one. It's open access from the McGovern Medical School. So you need to pass the message from your brain to your extremities, or from your skin back to your brain to serve as a feedback. So these are very, very long wires, no, from brain to periphery or from periphery back to the brain. So we can classify them into 3 to make it simple. If it comes from the brain and connects with the rest of the body, those are what we call the projection fibers, from the top going down. So these are the projection fibers. They can go not just to the extremities, but going to your viscera. So you learn this in 205 and 206. The butterflies in your chest or in your stomach because of this particular cranial nerve. So via connections from the brain or back to the brain, the hormones here, your neurotransmitters, will make you feel happy or sad or without any feeling at all if you're depressed. And then you have commissural fibers. Commissural fibers are connections between the two hemispheres. As I explained earlier, your dominant literate brain has to communicate with your non-dominant illiterate brain to form a cohesive understanding of what you're going through. So commissural fibers. So again, one of those dumb mnemonics from Dr. Pascual. So miss you or I miss you. You can use this as a way of remembering commissural fibers versus association fibers, which never leave the same hemisphere. So they only work within the same hemispheres to connect the different parts, like frontal with occipital, parietal with temporal, temporal with occipital, so on and so forth. So they never leave that hemisphere. Right? So they help to communicate. No? They help communications within the same hemisphere. Right. I showed you that website earlier, and maybe to make it even simpler, imagine cutting a brain as you would cut a hard-boiled egg. Of course, you know what a hard-boiled egg looks like. You've eaten balut. You've eaten hard-boiled egg, eaten soft-boiled egg. So you know that there's an egg yolk inside. And you know that the egg yolk doesn't really occupy the entire space inside that egg. That is the principle I'm trying to get at here for us to understand it when we slice brains. So when you slice a brain, as you can see, not all of the egg yolk is seen in all the cuts. The same thing with the ventricular system, the same thing with the basal ganglia. So there'll be parts where you don't see any gray matter at all. So we will get to this. No? So imagine your brain as a hard-boiled egg. These are the different neurons from different parts of your brain which sends down their axons, or they're receiving dendrites from below going up to the brain. Now, depending on where you cut it, so trigger warning, blood, that's a knife. So if I want to cut the brain here, I cut it here, I will not see any of the egg yolk yet. I will see only white matter. So the white matter which comes from this gray matter here will form a large mass of white matter, which we call a semi-oval center, if you want to go English on this. But anatomically, it's called the CSO, or the centrum semi-ovale. So better imagine like this, because that's the way it should be imagined. You're cutting through here. If you cut through here, you're not hitting any of the gray matter down here. So your centrum semi-ovale, this is a coronal view using an MRI. If you cut it through here, and here blown up for you, you cut it through here, this is what it looks like on an eggshell slice of a brain, whether it's an actual brain, a MRI brain, or a CT scan brain. You'll always get this particular cut above everything else, where it's all white matter. So this is the centrum semi-ovale. Now what if you cut it here? You cut it below the centrum semi-ovale, so you're hitting part of the lateral ventricles already here, and you're hitting some of the gray matter already. Then you should be seeing some parts of the gray matter and the chambers of the CSF as you go below. So as you go below, since that the fibers from above need to traverse that, they need to get around that lateral ventricle, they need to go around it, so they form a crown. This crown of white matter is known as the corona radiata. And landmark for the corona radiata, when you look at the ventricles, so this is area where the lateral ventricle was. So the fibers need to radiate around it to get to the CSO up here. So that radiating set of fibers is the corona radiata, which here a very nicely dissected specimen forms a crown as it penetrates through the gray matter here of the basal ganglia. So corona radiata at this level. So at this level, you're hitting some of the white matter. Some of the ventricular system, and you're hitting part of the gray matter already. So the appearance will be different from the one you saw earlier. So now you hit part of the ventricles and part of the basal ganglia here. And it looks, even on MRIs or especially on cat brains, you see the fibers no forming linear uh, diagonally, no. So that's the corona radiata once you're at this particular level. Now as you descend, as you're cutting through the gray matter inside, so you're hitting the egg yolk already, and you see part of the ventricular system, and this is where your white matter um, tends to hit its narrowest point. So they're trying to squeeze through the basal ganglia. This is now known as the internal capsule. So why they call it internal capsule, I'm not really sure of that. But it's like it's a stripe inside of white matter inside the gray matter. So this behind this gray matter is the internal capsule. So in this view, it's not shown because it's still hidden here by the gray matter. So it gets clamped by that gray matter inside the cerebral hemispheres. So you don't see it anymore. It's right here in between this gray matter here. So we need an eggshell cut to visualize what the internal capsule actually looks like. So if we cut it like this, coronal, you see the centrum semiovale, the corona radiata, now has to squeeze through in between that gray matter mass here inside. It goes between the egg yolk, splits it into two. So that is now what we call the internal capsule. So again, I do not know why it's called the internal capsule, but that's what it's named. So that band of white matter squeezing through is the internal capsule. This is a coronal slice. It's the same whether it's an MRI, a CT scan, or a cut brain. So if you look at it from an eggshell slice point of view, so here where it forms a kind of boomerang, that's your internal capsule, squeezing and finding its way through the basal ganglia. So that's internal capsule. So it forms a boomerang there. So like a boomerang, it has a arm in front, an arm behind, or a knee at the middle. So the first part, which is anterior, is called the anterior limb of the internal capsule, and the part behind is the internal limb of the posterior capsule of the internal capsule, posterior limb of the internal capsule, and where it bends is the knee. They call it a knee and not an elbow. So why am I showing you this? I'm introducing to you the internal capsule because when you get to the real world, most of the strokes where the people bleed because of uncontrolled hypertension or high blood pressure is unfortunately through here, where your white matter fibers are at its most vulnerable and most concentrated, instantly paralyzed without any movements at all because all of those fibers are concentrated back here. Right? So take away the basal ganglia. So this is what the internal capsule looks like. So centrum semiovale, and then you have the corona radiata, and squeezing through is the internal capsule. And this is what the newer technology shows us, the same thing as a very difficult dissection. So this is diffusion tensor imaging, where we colorify the white matter of the brain. So we discover new things every year. So putting it together, different slices of the white matter which descends or ascends into the brain, the cortex, the centrum semiovale becoming corona radiata becoming internal capsule, interspersed or squeezing its way through the gray matter inside, which is the basal ganglia. Right, so these are from Nolte, where the white matter has been stained for myelin, staining it black or blue. That's the centrum semiovale, becoming the corona radiata. So here you see the fibers, the lines there. That's where the fibers start to form a radiating pattern as you descend. And then as you go deeper and deeper where the gray matter are, so the gray matter will not stain with myelin stain. Hence you get the boomerang of the internal capsule. Okay, so boomerang. So more on that when we discuss in phase 2, when we discuss the importance of the structures. Right? So these are just flashed on your screen to show that there are different technologies to show which directions. So this posterior limb is where those motor fibers will pass through. That's why it's colored blue. So the bluish part here. So you don't need to spend so much time here. We can always revisit this when we discuss the meanings of the structures we've been introducing you to. Right? So just showing you where it comes from the pre-central gyrus down into the white matter, into the internal capsule, and then we will discuss this in the brainstem and when Dr. Seng talks to you about the spinal cord. Right? So this is just technology flashing it there. Then that question about why the occipital lobe went all the way back here, yeah, due to the differentiation and allocations, so it was pushed all the way back. Hence, the connections from the eyeball also had to lengthen, and the reason why they're shaped that way. So Dr. Baticolon will talk to you about the visual system next after a few weeks. Right, just flashing the pictures and then flashing the newer technology. Since it's a projection fiber, it goes from one part of the brain to another and beyond. Versus commissural fibers such as the corpus callosum. So this is a way of looking at via dissection. It is connecting right and left, temporal, frontal, parietal, all connected, and occipital via this corpus callosum. Again, don't need to remember all of this, it's just this we're focusing on. And this is diffusion tensor imaging, which uses color coding. Hence on diffusion tensor imaging, easier to identify the commissural fibers because they appear as red. So the red ones are the ones that are crisscrossing the midline to the left or right hemisphere. So that's your corpus callosum as it is meant to be visualized. So that's how it appears on one view. This is how it appears from above. And this is how it is meant to be seen. So it's a very wide connection from right to left. So just like anything that bends so far in neuroanatomy, so the part that bends in front is called the knee or the genu. So as in genuflect is the most anterior part. Then you have the more wider or the fatter portion, which is the splenium, for a reason, because it's really connecting your visual areas together. Hence, you need that to form a complete picture. And then the body, which is everything else actually, which connects the front and the back. So a smaller one, which we had a glimpse of earlier, is the anterior commissure. So depending on how the brain was sliced, you may or may not see this particular commissure since it's quite thin and small. But I'm mentioning it here because it's also a landmark for an important structure, which we will get to in a few weeks. So anterior commissure. So as you can see on the screen, it connects temporal with temporal. So a very minor commissural fiber. Right? So that's the anterior commissure in front in red. Smaller than the corpus callosum. So this slice is meant to show you both corpus callosum up here, and since it was not cut in a really symmetrical fashion, you have that anterior commissure here. Not seen here. I was just mentioning the structure here is more important for you in terms of learning. More than short-term memory, this is the part we will get through very, very soon. Very important for learning. That's what we do in neuroscience. Right? Other commissures are technically not part of the cerebral hemisphere anymore, but just mentioned here in fashion, in for completion purposes. The posterior commissure. We will not delve with this now. Right? Other association fibers, which I mentioned, which might be important, are located inside that cingulate gyrus. So just flashing here, don't need to spend so much time on this right now. So the cingulum, which on diffusion tensor imaging is not red, it is green, therefore it is a projection fiber, like the ones I'll show you earlier, going to the internal capsule. But to tell you how important that cingulum is without telling you what it does, look how very connective that area in the cingulum is. Gives you a clue why it is important in terms of who you are and what you do. Right? So flashing, flashing, flashing. I'm going to deal with this right now. There are other fibers which will not be relevant for you at this time as of for foundational neuroscience or for med school in particular. So this just flashed for completion purposes. Right? And before I leave, we have to deal with this one, which is still in the textbooks. The connection between that speech area here and the language area here in the temporal lobe, the so-called arcuate fasciculus. Just mentioning it here, you have to delete this from your knowledge since it's already disproven already. More on that when we revisit the cerebral cortex in a few weeks' time. Alright, so this is what I showed you earlier. Gray on the outside, white on the inside until it reaches the gray matter on the inside. So white matter that crosses the midline, a big one here, a smaller one here. Alright, so I'm not gonna delve with this anymore. That project I showed you earlier in that webpage is a child of this big brain, human brain project. So I hope some of this trickles down into your consciousness and eventually we'll get to this part of your brain that is most important for you as a person and as a medical student and as a doctor. Okay, so we end it here. Hopefully, a recording of this will make you remember it better. It's not always easy the first time. So thank you, and you can always send in questions through your liaison or through email. Okay, thank you very much.
Thank you so much, Doc.
Thank you, Doc.
Thank you.
Thank you po, Doc.